Alright, welcome back. So in the previous pages, we have covered how to construct a KT tree, as well as how to do a queries based on KT trees. And we also mentioned how to do the query based on the KT tree with high dimensions. Here, if we take a look at the KT tree we construct, actually the KT tree will partition the space into multiple subregions. And however, for subregion, the size of different subregions can be very different. Some can be very large, some can be very small, right? Also, the lines, they are not very organized. Because we are partitioned according to the density of the points. We want to partition one half of points on one side and the other half in the other side, right? Into half and half. However, in other words, the lines we partition the regions can be very different. We have one line here and one line here, right? They are not the same line actually. And this makes it very difficult for us to interpret the regions in such a space, which may cause some problems, right? This is one potential problem with the KT tree because it will partition the space into very random size regions. Another problem is that in the KT tree, if we look at the nodes inside the tree, each node will have two children nodes, right? In other words, we assign these pointers in the space as leaf nodes into a binary tree. So if we have lots of pointers in our database system, then the height of the tree will be about log n, right? In other words, if we have lots of pointers, the height of the tree will be very tall, right? And it will create some problems for us to do queries as well, because we have to do a query from the root until we reach in the leaf nodes. And because of these two disadvantages, and we would like to introduce another tree structure which can also be serving as a multi-relational index in database system as well, which is called a Coil Tree. Coil Tree has a very similar diagram as the KT tree we mentioned before. However, the Coil Tree also addresses the two disadvantages we mentioned above effectively. So Coil Tree will also partition space into different regions. However, for the Coil Tree, each node will be associated with squares. This square is very well organized, and nearby squares will also have the same size actually, which is very easy to interpret. So for the Coil tree, each node in the tree will be associated with 4 squares or 4 nodes. Also, in each partition, we will partition the region into 4 parts. Each part will be a square as well. So Coil tree was proposed by Raphael Frinker and John Bankney in 1974. So in the Coil tree, if a node is not a leaf node and its square is partitioned into 4 equal size squares associated with its children. For example, if we have a very large size overall, the square we show here, and for the root node, we partition this large square into 4 parts. This is one part, this is one part, this is one part, this is another part. Right. In other words, these 4 children nodes we mentioned here, they correspond to 1/4 of the larger square. This small square as shown here, right? So for the region we plan to do the further partition, we can further partition them into 4 parts as well, right? By drawing 2 lines. So similar, so and so forth, right? Until we can ensure each region will have one single data point. So if we look at the Coil tree, each node in the tree will be associated with 4 children nodes. It's not a binary tree anymore, right? It's 4 children tree instead. Also, for the size of the region corresponding to each node in the tree, they will also have the same size actually. This is another tree structure we can partition the such space into different regions for constructing a multidimensional index. Okay, so based on the previous description, we want to show how to construct a Coil tree in this page. So formally, this construction process will also be based on recursive function calls, right? So the Coil tree will be associated with the root, and this root will contain all the nodes or pointers in the set P, right? And the construction process of Coil tree will be based on recursive splitting of the space, and which will continue until there at most 1 or k points left inside each square. And at the bottom, we show how to construct a Coil tree by the first step, right? Now, given a large size of square as shown here, we can find the mid value of both x and y, right? And with these mid values, we can partition this large square into 4 parts. We have northeast, northwest, southwest, and southeast, right? So for each region, they have the data values or pointers, which are, either larger or smaller than the mid value of the x and y and the coordinates, right? In this way, we'll be able to partition the original region into 4 parts, and we do this recursive partition until this requirement is met, and there are at most 1 or k points left in each of the square. Okay, so compared with the KD tree, Coil Tree is relatively shorter because each node in the tree will have 4 children nodes. Also compared with the KD tree, the partition process, they will partition the space into equal size sub-region instead. Each one will be a square, which is relatively easier to interpret, also to look at, right, than compared with KD tree. And we'll provide a demo in this page, and let's look at how we do construction of the Coil Tree with the demo. Alright, so this is a demo provided by Google GitHub, and we have a space. We denote the search space we have, and we want to construct one Coil Tree depending on the data we provide in the space. And we can provide data points by clicking this space. For example, let me enlarge the page first for you. So we can click the region inside it, and it will create one data point inside it. If we click one single data point, right, it will have 1 point here. Because right now we have 1 single point in the region, then we can meet the requirements and we don't need to further partition it, right? However, here if we further create more data points into it, we can click one more point here, and we can partition this region into 4 parts, right? Each part will contain 1 single data point, right? Some may contain no data points at all. And here, as we create more data points into this region, for example, we can click one more point into this one, and we can do a further partition, right? And we can partition this region into 4 parts as well. Each one will contain 1 single data point. And here it will be very interesting if we click one point which is very similar or very close to the original point here. If so, then we will partition the region into very small size, because we have to ensure each region will have 1 single data point. And because these 2 points are very close, and we have to partition them into different squares, and then we create a very small square as shown in this page. And in a similar way, we can do the partition of the other regions as well, as we have more data points provided. And you can also try this by yourself after class to see how we do the construction Coil Tree and how can we play with this demo, so you can have a deeper understanding about this. Okay, so this is about Coil Tree in this section, and that's it for today's class. And we will plan to finish this section by the next week. We will have one more class on this. And next we will discover R tree, which is another tree structure diagram we can construct indexes in database systems. Okay, so thanks for your attention, and that's it for today.